February 21, 2023. The Antarctic summer minimum sea ice extent is measured by satellite. The number comes back 1,788 million square kilometers. For context, the 1981 to 2010 average for this period is approximately 284 million square kilometers. The 2023 minimum is not close to this average. It is not a standard anomaly, the kind that happens in a bad year, a few 100,000 square kilometers below the mean. It is more than 1 million square kilometers below that average, an anomaly roughly the size of Egypt, and the summer minimum was only the beginning. Through the autumn and winter of 2023, as the ice failed to recover at its normal pace, the anomaly grew much larger. By June, the missing sea ice had expanded to 233 million square kilometers, compared to the June average, twice the size of the previous June record. That winter anomaly was, according to analysis by the British Antarctic Survey, more than 5 standard deviations below the mean of the satellite record. In statistics, 5 sigma is the threshold p-physicists use for a discovery, the level at which a result is considered essentially impossible to have occurred by chance. The British Antarctic Survey's analysis found that the 2023 anomaly would occur roughly once in 2,000 years in a pre-industrial climate. The year before, 2022, had already set a record low for the summer minimum. Antarctica had broken its own record. The year after, 2024, set the second lowest summer minimum on record, tying 2022. And 2025 tied for second lowest again. The sea ice around Antarctica had been stable, actually growing slightly, from the late 1970s through 2015, while global temperatures rose. It was considered one of the curiosities of the climate system, the one major indicator that was not following the expected pattern. Scientists had explanations for why it was stable. Then, in 2016, it changed. Within 7 years, Antarctica went from growing sea ice to the most extreme low in the observational record. That is the first anomaly, the one that is at least partially explained now, though the explanation arrived after the fact. The second anomaly is smaller and closer, literally beneath the ice of the most studied glacier in the world. In May 2024, a team from the University of California, Irvine, published results in the Proceedings of the National Academy of Sciences using daily repeat satellite radar data from the ICEYE constellation. They were looking at the grounding zone of Thwaites Glacier, the place where the glacier transitions from resting on the seafloor to floating on the ocean. This transition, in every model of glacier dynamics for the past half-century, has been treated as a fixed boundary, a line. Ice on one side is grounded, ice on the other side floats. The boundary moves as the glacier retreats, but at any given moment, the boundary is a line, and the ocean and the glacier interact at that line. The ICEYE data showed something different. Seawater was not just touching the grounding line from the ocean side. It was pushing inland, under the grounded ice, at tidal frequencies, reaching as far as 6 kilometers past where the grounding zone itself sat. The boundary was not a line, it was a zone, and the ocean was getting into parts of the glacier that every model assumed were sealed from the sea. The UC Irvine team wrote, in their conclusion, that the results call into question the traditional approach of modeling a fixed, abrupt transition from grounded ice to ice floating in the ocean. They called into question one of the foundational assumptions of glacier dynamics modeling, and the third anomaly. As of mid-2026, published results confirm that Antarctica is melting from below at rates that scientists describe as worse than expected, not just in the already alarming West Antarctic Ice Sheet, but in East Antarctica, where the IC was supposed to be more stable. 3 anomalies. 3 things not following any known pattern. And the glaciologists and oceanographers studying Antarctica are increasingly direct about what they mean. The models used to project sea level rise are probably underestimating what is coming, because the physical processes driving the melt are more complex and more rapid than those models assumed. For decades, the scientific story of Antarctic glacier melt was a story of slow, steady, predictable deterioration. Ice loss was accelerating, yes, but in ways that the models tracked roughly. The sea level rise projections, while alarming, had error bars that researchers understood. The discoveries of the past 3 years have changed that story. Not because something unexpected has happened to Antarctica in some general sense. The ice was always going to melt in a warming climate, but because three specific physical processes, each of which was either unknown, poorly understood, or assumed to operate differently, have been confirmed to be operating in Antarctica in ways that make the melt faster, more extensive, and more difficult to predict than the standard models captured. The glacier melt happening in Antarctica right now is not following any known pattern, because the pattern was assembled from models that were missing pieces. The pieces are now being found. And each one that is found makes the picture more alarming. This video is about 3 specific scientific findings that, together, explain what it means to say that Antarctica's glacier melt is not following known patterns. The first is the sea ice anomaly. The collapse of Antarctic sea ice beginning in 2016 and reaching a catastrophic low in 2023, in a way that the climate models used by the IPCC failed to predict. That changed the ocean-atmosphere interaction across the Inti-Re Southern Ocean, and that has persisted through 2026. The second is the seawater intrusion discovery at Thwaites Glacier. The finding that seawater penetrates kilometers beneath the grounded ice at tidal frequencies, a process not included in standard glacier dynamics models, that makes the glacier more vulnerable to basal melting than any current sea level projection accounts for. The third is the confirmation of below ice melting at rates worse than expected, extending to East Antarctica as well as the already alarming West Antarctic Ice Sheet, in a pattern that the most recent models are being revised to incorporate. By the end of this video, you will understand what each of these findings actually shows, why the standard models missed them, what they mean for sea level rise projections, and why the scientific community is using language about Antarctica that, even 2 years ago, was confined to the most extreme scenarios. How did Antarctic sea ice grow for 40 years while global temperatures rose? And what actually caused the sudden collapse in 2016 that led to the 2023 anomaly? What exactly did the ICEYE satellite data show about Thwaites Glacier's grounding zone? And why does the seawater intrusion finding matter so much for sea level rise projections? Why is the distinction between the grounding line as a fixed boundary and as a dynamic zone so consequential for glacier dynamics models? What does the below ice melting sea formation actually mean, and how does it connect to the East Antarctica findings? And what is the specific gap between what current sea level rise projections say and what the 3 new findings suggest the actual trajectory might be? This is not a video claiming immediate catastrophic sea level rise. The Thwaites Glacier, even under pessimistic scenarios, is not projected to collapse within years or decades. The September 2025 summary explicitly states that a full Thwaites Sea is unlikely in the next few decades. This is also not a video that treats Antarctic glacier science as settled. The specific findings described in this video call into question assumptions that have been embedded in glacier dynamics models since those models were first constructed. Sea level rise projections, widely cited in policy discussions, are based on models that did not include the seawater intrusion mechanism, the dynamic grounding zone behavior, or the scale and persistence of the sea ice anomaly. These projections need revision, and the direction of that revision is toward more ice loss, faster. The honest version of this story is that what is happening in Antarctica right now is less well understood than the standard projections suggest, and that the specific processes being discovered are each pointing in the same direction. The ice sheet is more vulnerable to ocean interaction than previous models assumed. Before we continue, if the kind of science that explains specifically what is wrong with models rather than just saying, it's worse than we thought, is what you come to Galaxy Pulse for, subscribe. Now, back to Antarctica, and to the three processes that the standard models missed. The sea ice collapse, and what it changed base explanation. Antarctic sea ice is not the same thing as the Antarctic ice sheet. The ice sheet is the massive accumulation of land-based ice, kilometers thick in places, that sits on the Antarctic continent and that, if it melted, would contribute meters to global sea levels. Sea ice is the thin layer of frozen ocean water that forms and melts around the continent seasonally, typically reaching its maximum extent in September at the end of the Antarctic winter, and its minimum in February at the end of the summer. Sea ice has a much smaller direct effect on sea levels than land ice, because sea ice is already floating and its melting does not change ocean volume. But sea ice has enormous indirect effects. It reflects sunlight back to space, reducing the solar energy absorbed by the Southern Ocean. It insulates the ocean surface from the atmosphere in winter, moderating the heat exchange between the ocean and the air. It provides a protective buffer for the edges of ice shelves, the floating tongues of ice that extend from the ice sheet into the ocean, shielding them from wave action and from warm ocean water. And its formation drives one of the most important processes in global ocean circulation: the production of Antarctic bottom water, cold, dense water that sinks and drives a significant component of the global thermohaline circulation. To understand why the sea ice has these indirect effects, it helps to think through the physics. When sea ice forms, the ocean surface freezes, and the salt that was dissolved in the seawater is excluded from the ice crystals, concentrating into the remaining water below. This cold, salty, dense water sinks. It is denser than the water below it, driving the production of Antarctic bottom water. This deep water then flows northward along the ocean floor, eventually reaching every ocean basin on Earth, carrying its cold properties with it, and forming a critical component of the global ocean conveyor belt. Any change in sea ice extent, therefore, affects not just the Southern Ocean, but the global ocean circulation through this mechanism. If sea ice forms less extensively, less dense water is produced, the conveyor weakens, and the global ocean's ability to transport heat from equatorial to polar regions changes. The behavior of Antarctic sea ice, since satellite monitoring began in the late 1970s, was, until recently, one of the most puzzling features of the observed climate record. While Arctic sea ice declined dramatically as global temperatures rose, Antarctic sea ice remained stable and even grew slightly through about 2015. Climate models predicted that Antarctic sea ice should be declining. The observations showed it growing. This discrepancy was the subject of substantial scientific debate, with various explanations proposed involving wind patterns, ozone depletion, and changes in ocean stratification. Then, in 2016, the pattern changed. The stability of Antarctic sea ice ended abruptly. Over the next 7 years, sea ice extent declined significantly. The summer minimum broke records in 2022, then broke them again in The Antarctic sea ice has not recovered to anything approaching its historical average since Aditya Narayanan, a physical oceanographer at the University of New South Wales and the University of Southampton, described the situation in 2026 in terms that capture the scientific community's position precisely. The system is behaving in a different ma-en-ner. Obviously, something has changed under the standard expectation derived from climate models. The decline of Antarctic sea ice in a warming world was expected to be gradual, roughly proportional to the increase in temperatures, and trackable by the models that projected it. The IPCC's Climb 8 models, the CMIP-6 ensemble used in the 6th assessment report, projected Antarctic sea ice decline at rates consistent with the expected physical response of sea ice to ocean and atmosphere warming. What happened between 2016 and 2023 was not gradual and was not captured by these models. A study by Rachel Diamond and colleagues at the British Antarctic Survey, published in 2024, assessed whether the CMIP-6 models could reproduce the 2023 anomaly. The conclusion was specific. CMIP-6 models rarely simulate Antarctic winter sea ice anomalies as large as observed in 2023. The models that underlie the current generation of climate projections do not, in their normal operation, produce events of the magnitude of what actually occurred. The 5 standard deviation winter anomaly of 2023 was, according to the BAS analysis, a 1 in 2,000 year event in the pre-industrial climate. Climate change made it 4 times more likely. But even with this increased probability, the event was far outside the range of what the standard models had been projecting as plausible near-term outcomes. Something about the physical system in Antarctica transitioned in a way that the models did not capture. The sea ice that had been growing for decades despite global warming suddenly began losing ice at catastrophic rates. The transition was abrupt in a way that suggests a regime change rather than a gradual response to warming, and the system has remained in the new, lower ice state through 2024 and 2025 without recovery. The 3-phase collapse and its consequences research published in Science Advances identified 3 distinct phases in the Antarctic sea ice decline between 2013 and 2023. The first phase was the disruption of the Southern Ocean's layered structure by wind changes. The Southern Ocean maintains a distinct stratification: cold, relatively fresh water near the surface, with warmer, saltier water below. This stratification keeps the warm, deep water separated from the surface where sea ice forms. Changes in the southern annular mode, the dominant pattern of atmospheric circulation around Antarctica, caused wind anomalies that disrupted this stratification, mixing the layers and bringing warmer water toward the surface. The second phase was the ocean surface warming that resulted from this mixing. Warmer ocean surface water melted sea ice more rapidly, and the reduced sea ice cover changed the surface properties of the Southern Ocean. Instead of a white, reflective sea ice surface, the ocean was darker open water, absorbing more solar energy. This is the ice albedo feedback. Less ice means more absorption of solar energy, means more warming, means less ice. The third phase was the persistence of the new state. Once the transition occurred, the feedback loop between reduced ice cover and increased ocean heat absorption established a new equilibrium at lower sea ice extent. The system did not simply drift back to its previous state when the wind anomalies that initiated the transition relaxed. It settled into a new regime. The December 2024 Nature paper, led by Simon Josie at the National Oceanography Center, Southampton, documented what happened to the Southern Ocean and the atmosphere when the sea ice disappeared. In the regions of strongest sea ice loss, primarily in the Weddell, Bellingshausen, and Ross Seas, ice concentration was reduced by up to 80%. This produced an unprecedented doubling of mid-winter ocean heat loss to the atmosphere in those regions. Peak heat loss shifted from late April to mid-June. Atmospheric storm frequency increased. Dense water formation was enhanced, with implications that remain unclear for Antarctic bottom water production and global ocean circulation. The paper described the changes as substantial alterations to Southern Ocean atmosphere interaction. Each of these changes feeds back into the broader system. Changes in dense water formation affect ocean circulation that in turn affects where warm water is transported beneath ice shelves. Changes in storm frequency affect wave action that reaches ice shelf edges. The sea ice collapse was not just a sea ice event. It was a reorganization of the Southern Ocean atmosphere system. And one of the specific consequences of reduced sea ice is increased access for warm ocean water to the floating ice shelves and the glaciers they protect. The ice shelves around Antarctica, including the Thwaites Ice Shelf, are partly protected from warm ocean incursion by the sea ice that forms in front of them. When that sea ice is absent, the warm water that was previously blocked from reaching the ice shelf now has an open path. The sea ice loss and the accelerated basal melting of ice shelves are not independent processes. They are connected. Three concepts need to be clear. The first is what marine ice sheet instability is and why it is the central concern in Antarctic glacier science. The West Antarctic Ice Sheet sits on bedrock that is, in many places, below sea level. The glacier flows from inland areas down to the coast, and where the bedrock is below sea level, the glacier eventually becomes buoyant, floats, and becomes an ice shelf. The transition point between grounded glacier and floating ice shelf is the grounding line. The specific vulnerability of a marine ice sheet is related to the geometry of the bedrock. In many parts of the West Antarctic Ice Sheet, the bedrock deepens as you move inland, away from the coast. This means that if the grounding line retreats inland, the ice at the new grounding line is resting on deeper bedrock, where it is easier for it to become buoyant and float. As more ice floats, more of it is accessible to ocean melting. A retreat of the grounding line can be self-reinforcing. Retreat makes more ice float, floating ice melts faster, more grounding line retreat occurs. This is marine ice sheet instability, and it is why Thwaites and the West Antarctic Ice Sheet, more broadly, are treated as a potential tipping point in the Earth's climate system. The self-reinforcing character of this instability is what makes it so concerning. In most environmental systems, there are negative feedbacks that resist perturbation and return the system to its previous state. A warming ocean melts more ice, but the meltwater cools and freshens the ocean, reducing the temperature difference that drives the melting, a negative feedback. Marine ice sheet instability is a positive feedback loop. The retreat makes the system more susceptible to further retreat, not less. Once initiated above a certain threshold, the retreat does not stabilize. It continues until the geometry of the bedrock changes enough to provide a new point of stability, a ridge or shallowing of the bedrock that stops the grounding line from retreating further. In the case of Thwaites, the bedrock topography does not provide such stopping points for a very large area inland of the current grounding line position. The second is what the grounding zone's seawater intrusion finding changes. The standard model of glacier-ocean interaction at the grounding line assumes a sharp boundary. Grounded ice on one side, ocean on the other, with melting occurring at the boundary. The UC Irvine PNAS paper found instead a grounding zone, 2 to 6 kilometers wide, where the ice is tidally influenced, and where seawater penetrates beyond the grounding zone itself by another 6 kilometers inland at spring tide. This means that the ocean is melting ice that was previously considered fully grounded, and therefore fully buffered from oceanic influence. The models that project glacier retreat rates and sea level contributions from Thwaites were calibrated, assuming the fixed boundary model. They need to be revised to include the wider zone of ocean contact that the IceSide data revealed. A follow-up PNAS paper published in November 2025 confirmed that on March 10-12, 2024, the grounding zone and the 6-kilometer seawater intrusion zone became fully connected, forming a continuous 12-kilometer ice-ocean contact region. The process is not anomaly persistent but expanding. The third is why the subglacial water system beneath Antarctica matters for melt rates. Beneath the Antarctic ice sheet, a complex network of subglacial lakes and rivers exists, maintained by the geothermal heat from the bedrock and by the pressure-induced melting at the base of the ice. Water flowing through this system lubricates the base of the ice, reducing friction and allowing the ice to flow faster toward the coast. The February 2025 paper, generating the first complete dataset of water flow beneath the entire Antarctic ice sheet, was significant because this subglacial hydrology feeds directly into the ocean interaction at the grounding zone. Understanding how water moves beneath the ice is part of understanding how the glacier will retreat. Here is why these three anomalies together matter for the numbers that most people think of when they think of Antarctic sea level contribution. The standard sea level projections from the IPCC's 6th Assessment Report, published in 2021, estimated that Antarctica would contribute somewhere between 3 and 28 centimeters to global sea level rise by 2100 under intermediate warming scenarios. The wide uncertainty range, a factor of nearly 10, reflects genuine scientific uncertainty about how the ice sheet will respond. The three findings described in this video all point toward the high end of that range, or potentially beyond it. The seawater intrusion beneath Thwaites means that the rate of basal melting is higher than the models assumed. Because the contact area between warm ocean water and the glacier base is larger than the fixed boundary model described. This directly increases the rate at which grounded ice becomes buoyant, and therefore the rate of grounding line retreat. The sea ice loss means that warm ocean water has greater access to ice shelf fronts, reducing the buttressing that ice shelves provide to the glaciers behind them. Thinner, faster melting ice shelves buttress the glacier less effectively, allowing the glacier to flow faster toward the ocean. The confirmation of below ice melting worse than expected, including in East Antarctica, means that the uncertainty about the East Antarctic ice sheet, which contains far more ice than the West Antarctic ice sheet and was previously considered more stable, is substantially greater than the standard projections assumed. The September 2025 summary, the final output of a 7-year, $50 million international research program specifically focused on Thwaites, is explicit. Retreat has accelerated considerably over the past 40 years. Further and faster retreat through the 21st and 22nd centuries is set to occur, and general collapse of the West Antarctic ice sheet cannot be ruled out. Cannot be ruled out is not alarming framing. It is the careful language of scientists who, having looked as closely as any team has ever looked at this specific system, are describing the boundary of what they can confidently exclude from the range of possible futures. The sea ice anomaly is partly explained. The three-phase mechanism is documented. The consequences for Southern Ocean circulation and ice shelf access are being studied. But one aspect of the 2023 anomaly remains genuinely unresolved. Why the transition happened when it did, and whether the sea ice will eventually recover toward its historical average or has entered a new, permanently lower ice regime. This unresolved question matters for everything downstream: the warm ocean, access to ice shelves, the buttressing of glaciers, the rate at which the grounding lines of Thwaites and its neighbors will retreat in the coming decades. The specific mechanism that connects the southern ocean's changed state to the glacier dynamics beneath the Thwaites ice shelf is the subject of the most recent detailed measurements, including a multi-year oceanographic time series collected through boreholes beneath the Thwaites eastern ice shelf from 2020 to 2023. What those instruments found about the dynamics of the cavity beneath the ice shelf, and how it connects to the broader changes in the Southern Ocean, is the next layer of the story. Thwaites, the grounding zone, and the models that missed it. Thwaites Glacier is the widest glacier in the world, approximately 120 kilometers across at its calving front, the edge where ice breaks off into the ocean as icebergs. It drains a catchment area roughly the size of Florida. The ice it contains, if melted, would raise global sea levels by approximately 0.6 meters. That number, 0.6 meters, is the contribution from Thwaites alone, but Thwaites is not isolated. It sits at the edge of the West Antarctic Ice Sheet, and its retreat affects the stability of neighboring glaciers and the broader ice sheet. The potential sea level contribution from the full West Antarctic Ice Sheet, if the marine ice sheet instability described earlier were to propagate through the basin, is estimated at more than 3 meters. This is why Thwaites is described as a linchpin. It is the point at which the WISE is most vulnerable to rapid retreat, and its behavior largely determines the behavior of the broader system. To understand why Thwaites is uniquely important, it helps to think about the geometry of the West Antarctic Ice Sheet. The ice sheet's interior is connected to the ocean at multiple points around its perimeter, through outlet glaciers that flow through montane valleys and topographic channels toward the coast. Most of these outlets are bounded by mountain ranges or bedrock ridges that physically constrain the glacier's width and limit how quickly ice can flow out. Thwaites has no such constraint. Its catchment area opens into a vast basin of ice extending hundreds of kilometers inland, with bedrock that deepens as you move away from the coast. If the grounding line retreats past the current position, there is no obvious topographic barrier to stop it from retreating much further. The glacier is wide, the ice behind it is thick, and the bedrock geometry is exactly the configuration that marine ice sheet instability theory predicts will sustain self-reinforcing retreat. Thwaites is already losing more than 50 billion tons of ice to the ocean each year, equivalent to about 4% of annual global sea level rise. Since the 1990s, the amount of ice flowing out of the Thwaites Basin has nearly doubled. The grounding line has retreated inland at observable rates. These are not projections of future change. They are measurements of what is already happening. The International Thwaites Glacier Collaboration, a 7-year program funded jointly by the U.S. National Science Foundation and the UK Natural Environment Research Council, involving more than 100 scientists, published its comprehensive summary in September 2025. This document, representing the final output of the largest coordinated scientific effort ever focused on a single glacier, deserves to be quoted precisely. Thwaites Glacier's retreat has accelerated considerably over the past 40 years. Although a full collapse is unlikely to occur in the next few decades, our findings indicate it is set to retreat further, and faster, through the 21st and 22nd centuries. and general collapse of the West Antarctic Ice Sheet over this timeframe cannot be ruled out. Further research is urgently needed to refine this timeline. This is not doomsday framing. It is science. The scientists, who spent 7 years drilling through the ice, deploying ocean sensors in the subshelf cavity, mapping the bedrock beneath the glacier, and analyzing decades of satellite data, reached these conclusions as the best current summary of what the evidence shows. The UC Irvine P. Nass paper, published in May 2024, led by Eric Rignot and colleagues, is technically complex, but its implications are straightforward. The ocean is getting under Thwaites much further than models assumed. The method was enabled by a new observational capability, the ICEYE satellite constellation, a fleet of small synthetic aperture radar satellites that can make daily repeat observations of the same location, provided a continuous time series of radar data from March to June 2023, capturing the grounding zone of Thwaites at high temporal resolution. Synthetic aperture radar is sensitive to very small surface motions of the ice, allowing the team to detect the tidal flexing of the glacier at the grounding Z1 and to map where that tidal influence extends. What they found has two components. The first is the grounding zone itself, a 2 to 6 kilometer wide band where the ice is tidally influenced, and the boundary between grounded and floating ice migrates with each tidal cycle. At high tide, the ocean pushes further inland. At low tide, it retreats. This grounding zone was wider than standard models assumed, and its width varies with the local bed topography. 6 kilometers in the central part of Thwaites where the bed is shallow, 2 kilometers along the flanks where the bed is steep. The second component is the seawater intrusion beyond the grounding zone itself. In a bed depression located on the inland side of a bedrock ridge, seawater was penetrating at spring tide to a distance of 6 kilometers beyond the grounding zone. The intrusions were 5 to 10 centimeters thick. They appeared at tidal frequencies. They were reaching ice that every model of glacier dynamics treated as fully grounded and fully buffered from oceanic influence. Rignot and colleagues described the implications directly. The rushing of seawater beneath grounded ice over considerable distances makes the glacier more vulnerable to melting from a warmer ocean than anticipated, which in turn will increase projections of ice mass loss. A follow-up PNAS paper from November 2025 documented that on March 10-12, 2024, the grounding zone and the 6-kilometer seawater intrusion zone became fully connected, forming a continuous 12-kilometer ice-ocean contact region. The process that was first documented in 2023 data has continued expanding in 2024. The models that project Thwaites' retreat rate were not calibrated to include this extended zone of ocean contact. Revising them to include it will produce faster retreat rates and larger sea level contributions than the current projections show. For most of the history of Antarctic glacier science, the primary concern was West Antarctica. The WISE sits on bedrock below sea level, is subject to marine ice sheet instability, and contains enough ice to raise sea levels by several meters. East Antarctica, the much larger portion of the continent, was considered more stable, higher elevation, colder, resting on bedrock above sea level in most places, and less directly exposed to the warm ocean water circulating in the Amundsen Sea that has been destabilizing the WISE. The distinction between East and West Antarctica in terms of stability is real, but it is partly a matter of degree. East Antarctica does have regions where the bedrock is below sea level and where ice shelves rest on ocean water. The Totten, Moscow Univ R City, and Wilkes Basin sectors are examples. These sectors have been recognized as potentially vulnerable to marine ice sheet instability, but they were generally considered less immediately threatened than the Ys because the warm ocean currents that have penetrated the Amundsen Sea and are driving Ys melting have not, to date, penetrated in the same way to East Antarctic ice shelves. The cold water barrier, colder surface water that keeps warm circumpolar deep water away from ice shelf fronts, has, so far, been more effective in most East Antarctic sectors than in the Amundsen Sea. Recent findings have complicated this picture significantly. In November 2025, scientists published evidence of a dramatic meltdown that occurred in East Antarctica approximately 9,000 years ago. During this ancient event, warm, deep ocean water surged beneath the region's floating ice shelves, driving ice loss at a rate that was, in the context of the Holocene, remarkably rapid. The study documented that this event was not an isolated, local phenomenon, but was widespread across East Antarctic coastal margins. This matters because 9,000 years ago is relatively recent in geological terms, and the ocean temperatures of that period, while warmer than the pre-industrial baseline, were not dramatically different from current conditions. The warm ocean water that drove the ancient East Antarctic melting was not from some exotic past climate state. It was from conditions that current and projected warming is approaching. The significance for the present is that the physical mechanism, warm deep water penetrating beneath East Antarctic ice shelves, is the same mechanism that is currently operating in the Amundsen Sea against the Ys. If this mechanism was capable of driving large-scale East Antarctic ice loss 9,000 years ago, when the ocean and atmosphere configuration allowed warm water access, the question of whether current warming could eventually enable similar access to East Antarctic ice shelves becomes considerable, why more relevant. The own summary explicitly frames this connection in its call for climate mitigation. Immediate and sustained climate change mitigation, decarbonization, offers the best hope of delaying this ice loss and avoiding initiation of similar unstable retreat in marine-based sectors of East Antarctica. This language implicitly acknowledges that the threat of Ys-like dynamics spreading to East Antarctica is a concern that warrants active climate mitigation, not just passive monitoring. East Antarctica contains approximately 52 meters of sea level equivalent in ice, far more than the West Antarctic Ice Sheet. Even a small percentage of East Antarctic ice, mobilized through marine ice sheet instability, would represent sea level contributio ns that dwarf what is currently projected from Thwaites, or the full Ys. The finding that this ice was capable of rapid loss through ocean-driven mechanisms 9,000 years ago adds a new and sobering dimension to the long-term picture. There are three interpretive frames for what the three anomalies, the sea ice collapse, the seawater intrusion, and the below ice melting, collectively represent. The first frame is the observational advance frame. In this view, the primary story is methodological progress. New satellite capabilities, including the ICEYE constellation and improved radar interferometry, are revealing physical processes that previous observations could not detect. The Antarctic sea ice anomaly was observed with the same satellite passive microwave instruments that have been measuring sea ice since 1979. The seawater intrusion beneath Thwaites required daily repeat synthetic aperture radar coverage that only became possible with the ICEYE constellation. Better observations are revealing a more complex system than the models assumed. The second frame is the model gap frame. In this view, the three anomalies represent specific gaps in the physical models that are used to project sea level rise. The CMIP-6 models do not reproduce the 2023 sea ice anomaly. The glacier models do not include the extended grounding zone and seawater intrusion process. The ice sheet models were not calibrated to the subglacial hydrology revealed by the February 2025 dataset. Each gap, individually, introduces uncertainty into the projections. Together, they suggest that the physical processes driving Antarctic ice loss are more complex and potentially faster than the models capture. The third frame is the trajectory frame. In this view, each new observation is a data point in a trajectory that has been moving in one direction for decades. The grounding lines of the major glaciers in the Amundsen Sea embayment have been retreating. The retreat has accelerated. The sea ice that was growing has collapsed. The ocean beneath Thwaites is reaching parts of the glacier that were previously considered protected. The East Antarctic ice that was considered stable is now being investigated for water access. At every step, the system is proving more vulnerable than the preceding model assumed. All three frames are simultaneously valid. The observations are better. The models have specific gaps. The trajectory is concerning. Understanding what is happening in Antarctica right now requires holding all three frames, without collapsing any of them, either false reassurance or unfounded alarm. What the three anomalies together demonstrate is that the scientific community's understanding of how Antarctica's ice will respond to ongoing warming is incomplete in specific identified ways, and that the direction in which each identified gap points is toward more ice loss, faster than current projections capture. A note on what synthetic aperture radar enabled the seawater intrusion discovery beneath Thwaites depended on a specific technology. Daily repeat synthetic aperture radar from the ICEYE satellite constellation. Understanding what this technology does and why it was necessary illuminates why the Diskov Uri came when it did rather than earlier. Synthetic aperture radar, or SAR, is a remote sensing technique that uses microwave radar pulses to image the Earth's surface. Unlike optical cameras, which are blocked by clouds and require daylight, SAR penetrates cloud cover and works in polar darkness. More importantly, SAR can measure very small changes in the position of the Earth's surface with millimeter-scale precision, a capability called interferometry, which uses the interference pattern between two radar images taken at different times to detect CT surface motion. At Thwaites' grounding zone, the surface of the ice moves with the tide. At high tide, when the ocean pressure beneath the ice increases, the ice surface rises slightly. At low tide, it falls. These movements are tiny, centimeters, but they are precisely what SAR interferometry can detect. By analyzing the pattern of tidal motion across the grounding zone, the UC Irvine team could map where the ice was responding to tidal forcing and where it was not. The boundary between tidally influenced and non-tidally influenced ice is essentially the boundary between floating ice and grounded ice. The width of the tidally influenced zone is the width of the grounding zone. Previous SAR missions could make interferometric observations of Thwaites, but not with daily repeat frequency. The ICEYE constellation, operating as of 2023, was the first to provide daily repeat SAR coverage of the same location on the ground. This is THE enabling observation, the ability to track the tidal cycle of the grounding zone as it happens, rather than sampling it occasionally and trying to reconstruct the tidal signal from sparse data. The result: a continuous 3-month record of tidal motion across the grounding zone, from March to June 2023, revealed that the tidally influenced zone was 2 to 6 kilometers wide, and that seawater was penetrating an additional 6 kilometers beyond it. His is information that was present in the physical system before March 2023. It had been happening with every tide for years or decades. The ISI data was the first observation capable of detecting it. This is what "the pattern is only now being found" means in a specific, technical sense. The physical process was operating. The observation capability to detect it did not exist until 2023. The discovery represents the intersection of a real physical process and a new observational tool, not the beginning of a new physical process. The seawater has been reaching 6 kilometers beneath the grounded ice for as long as the tidal cycle has been operating at the current grounding line position. What is new is no wing it. Return to core question, let's come back to where we started. 3 things not following any known pattern. Antarctic sea ice that grew for 40 years through rising global temperatures, then collapsed abruptly in 2016, reached a 5 standard deviation winter anomaly in 2023, and has not recovered. With the summer minimums of 2024 and 2025, both among the 4 lowest on record. Seawater, pushing 6 kilometers beneath the grounded ice of Thwaites Glacier at tidal frequencies, in a process that the models used to project sea level rise were not built to include. With a follow-up study finding that by March 2024, Thwaites' 6-kilometer zone had connected to the grounding zone to form a continuous 12-kilometer ice-ocean contact region, and melting from below at rates worse than expected. Documented not just in the vulnerable West Antarctic Ice Sheet, but with paleoclimate evidence pointing toward East Antarctica's potential for similar ocean-driven instability. Each of these is a specific physical process. Each has been documented in peer-reviewed research. Each represents a gap in the models that project how much Antarctica will contribute to sea level rise over the coming century. The title of this video says the melt is not following any known pattern. The more precise statement is that the melt is following physical patterns that are now being characterized for the first time, and those patterns are making the system more vulnerable than the previously known patterns described. What the headlines missed coverage of Antarctic glacier melt falls into a consistent failure mode. It reports dramatic numbers. Thwaites could raise sea levels by 65 centimeters. Antarctic sea ice at record low, without explaining the specific physical mechanisms that make those numbers real or the specific gaps in the models that make the uncertainties large. Here are the specific things that most popular coverage has missed. The sea ice anomaly's relationship to model failure. The 2023 sea ice anomaly was not just a record. It was an event that the CMIP-6 models, the models underlying the IPCC 6th Assessment Report, do not reproduce in their standard operation. CMIP-6 models rarely simulate Antarctic winter sea ice anomalies as large as 2023. This means that the current generation of climate projections was not calibrated to reproduce the most extreme Antarctic sea ice event in the observational record. Popular coverage of THE 2023 record reported that a record had been set. It almost never reported that the models used for climate projections had failed to predict the magnitude of the event. The grounding zone as a dynamic zone rather than a fixed line. The PNAS seawater intrusion paper calls into question the traditional approach of modeling a fixed, abrupt transition from grounded ice to ice floating in the ocean. This is not a minor technical detail. The fixed boundary assumption is embedded in glacier dynamics models that have been used for decades. Every sea level projection that includes a Thwaites contribution was generated using models that treated the grounding line as a fixed boundary. The revision required by the seawater intrusion finding, and confirmed by the March 2024 data showing a fully connected 12-kilometer zone, has not yet been fully incorporated into the published sea level projections that policy discussions draw on. The connection between sea ice loss and ice shelf melting. The loss of sea ice provides warmer ocean water with greater access to ice shelf fronts. The sea ice loss and the glacier melting are not independent. They are connected through the same ocean circulation changes that are driving both. Popular coverage treats them as separate stories, discussing Antarctic sea ice in one article and Thwaites Glacier in another, without connecting the mechanism by which one accelerates the other. The East Antarctica finding from November 2025. The evidence that warm deep ocean water drove large-scale East Antarctic ice loss 9,000 years ago, in circumstances with some parallels to current warming, received modest specialist coverage and essentially no popular science coverage. The relevance of this paleoclimate finding to current vulnerability assessments of East Antarctica was not communicated. And the September 2025 summary. The 7-year, 50 million International Thwaites Glacier Collaboration published its comprehensive findings in September 2025. The findings, including that retreat has accelerated considerably, that further and fast retreat through the 21st and 22nd centuries is set to occur, and that wise general collapse cannot be ruled out, were the most authoritative scientific assessment of Thwaites ever produced. They received some specialist coverage and inadequate popular sea overage. The latest data, and what it shifts the most significant pieces of recent data for understanding the current state of Antarctic ice loss, are the February 2025 subglacial water model, the September 2025 summary, the November 2025 East Antarctica paleoclimate finding, and the subsequent sea confirmation that below ice melting is occurring at rates worse than expected. The February 2025 dataset of water flow beneath the entire Antarctic ice sheet, the first ever produced, was described by its authors as leading to more accurate projections of sea level rise. The significance is not just that a new dataset exists, but the subglacial hydrology it describes is a critical input to models of glacier dynamics that affects how fast ice flows toward the ocean and how the grounding line responds to changes in ocean pressure. Models that include this more complete picture of subglacial hydrology produce different, and likely higher, estimates of ice loss rates. The September 2025 summary represents the scientific community's most current and most carefully assembled picture of where Thwaites is going. The explicit statement that retreat through the 21st and 22nd centuries is set to occur faster, and that WAIS general collapse cannot be ruled out, represents a shift from the careful hedging that characterized earlier communications toward a more direct characterization of what 7 years of intensive study has shown. The also explicitly states that immediate and sustained climate change mitigation offers the best hope of delaying this ice loss and avoiding initiation of similar unstable retreat in marine-based sectors of East Antarctica. The November 2025 East Antarctica paleoclimate finding adds a longer-term dimension. East Antarctica contains roughly 52 meters of sea level equivalent in ice. The ice is not going to melt on any human timescale in its entirety. But the finding that warm ocean water incursion beneath East Antarctic ice shelves drove significant ice loss 9,000 years ago, in conditions that may be reproduced as Antarctic circumpolar current dynamics change under future warming, extends the zone of meaningful vulnerability beyond what the current generation of sea level projections generally includes. The November 2025 PNAS follow-up paper on Thwaites' grounding zone found that the 6-kilometer seawater intrusion documented in the 2024 paper had by March 2024 connected to the grounding zone itself, forming a continuous 12-kilometer zone of ocean ice interaction. The process is expanding, not stabilizing. The direction of travel is consistent across all of these datasets. More ice-ocean contact, more complex physical processes than the models assumed, and a trajectory that the IT summarizes as set to retreat further and faster. What this means for the future, the implications of the three anomalies for sea level rise projections, and for infrastructure and policy decisions, fall into several categories. For the sea level rise projections themselves, the three findings each identify specific processes that the current generation of models do not fully include. The revision of these models to incorporate the dynamic grounding zone, the extended zone of sea-water ice contact, the improved subglacial hydrology, and the updated understanding of East Antarctic vulnerability will produce new projections. The direction of the revisions is toward higher sea level rise, potentially pushing the upper end of current projections higher. For coastal planning and infrastructure, the relevant question is not which single projection to use, but how to account for uncertainty in a way that is appropriate to the scale of the stakes. Sea walls, tidal barriers, port infrastructure, and coastal development are built on decades-long time horizons. The specific revision that the seawater intrusion finding and the conclusions require for sea level projections has not yet been incorporated into the infrastructure planning guidance used by coastal sea communities and governments. Communicating the direction and magnitude of the model revisions that these findings require is a significant science communication challenge. For Antarctic research, the three anomalies have each identified specific scientific priorities. The sea ice anomaly requires better understanding of why the 2015-2016 transition occurred and whether it is permanent or reversible. The seawater intrusion, finding, requires validation of the process across other Antarctic grounding zones, beyond Thwaites, and incorporation into the next generation of glacier dynamics models. The East Antarctica findings require expanded monitoring of oceanographic conditions at East Antarctic ice shelf fronts to detect whether warm water incursion is developing there at a rate that would accelerate the existing timelines. There is also a specific concern that deserves mention. The IAE program, which funded the 7 years of research that produced the most comprehensive assessment of Thwaites ever undertaken, was set to wind down by year-end 2026. Proposed U.S. federal budget cuts to polar science, including potential cancellation of the research icebreaker, Nathaniel B. Palmer, threaten to reduce the observational capabilities on which continued monitoring depends. The scientific community, that has spent years building the monitoring infrastructure needed to track these changes, is facing a period of reduced, rather than expanded resources. Here is what the three anomalies together reveal at the deepest level. The sea level rise projections from the IPCC's Sixth Assessment Report, released in 2021, are the product of models calibrated on the physical understanding of Antarctic ice sheet dynamics that existed at the time of their construction. They represent the best science available when they were made. They are used by governments, coastal planners, infrastructure engineers, and development banks to make decisions that will shape how coastal communities respond to sea level rise over the coming decades. Those projections were made using models that did not include the seawater intrusion process beneath Thwaites. They were made before the 2023 sea ice anomaly, demonstrated that the Southern Ocean system can transition to a new, lower ice state, in ways the models did not reproduce. They were made before the 7-year program concluded that retreat through the 21st and 22nd centuries is set to be faster than previously projected, and they were made before the East Antarctica paleoclimate finding suggested that the stability of the East Antarctic Ice Sheet under warm ocean conditions is less robust than assumed. Each of these inputs, if incorporated into revised models, would shift the sea level projections. The direction of each shift is the same, toward more ice loss, more sea level rise, and less certainty in the timeline. The specific magnitude of the shift is not yet known. The models need to be revised. The revisions are underway. But the signal from the three anomalies, each pointing in the same direction, is clear enough that the scientific community is using language about Thwaites and Antarctica that, as recently as 2020, was confined to the most extreme and least likely scenarios. It is worth dwelling on the specific mechanism by which the models failed to capture these processes, because it reveals something important about how scientific understanding of complex systems advances. The seawater intrusion process was not unknown in principle. Tidal forcing at grounding zones was a recognized phenomenon. But the detection of its actual extent, 6 to 12 kilometers of continuous ocean ice contact, required the kind of daily repeat high-resolution satellite data that the ICEYE constellation only made possible in 2023. Before that data existed, the models incorporated tidal effects at the grounding zone as a minor perturbation rather than as a potentially dominant process. The observation revealed that the perturbation was not minor. The sea ice anomaly was similarly not unknown as a physical possibility. Rapid sea ice transitions had been modeled in idealized settings, but the CMIP-6 ensemble, the collection of about 40 different climate models from institutions around the world, did not reproduce events of the 2023 magnitude as anything other than extremely rare tail outcomes. The observation showed that the system was capable of producing these events at a frequency the models did not capture. This is a model calibration failure, and it is significant because these same models are used to project what the sea ice will do over the coming decades. The subglacial hydrology dataset is the most recent piece. The Antarctic ice sheet's plumbing, the lakes and rivers of liquid water beneath kilometers of ice, affects how quickly ice flows toward the ocean and therefore affects the rate of grounding line retreat. The first complete dataset of this plumbing was published in February 2025. Every ice sheet model run before that date was making assumptions about the subglacial hydrology without this comprehensive dataset to calibrate against. Whether those assumptions were systematically too conservative or too aggressive is one of the things the revised models will reveal. Cannot be ruled out is what scientists say when they have looked hard at something and found they cannot exclude it. The ICEYE looked hard at the West Antarctic Ice Sheet for 7 years. They cannot rule out its general collapse. That is not a statement of certainty. It is a statement about the limits of what evidence-based exclusion is currently possible for a system that is proving more complex and more vulnerable than any of the models that generated the current projections assumed. This is what it means to say that the glacier melt happening in Antarctica right now is not following any known pattern. The patterns are being discovered, and the patterns being discovered are each, in their different ways, revealing a system that is more exposed to ocean interaction, more sensitive to warming, and more capable of rapid change than the scientific understanding that underpins current sea level projections captured. The discoveries are not finished. The models are not yet revised. The projections are not yet updated, and the ice is melting now in ways those models did not predict. There is one more thread in this story. The sea level rise that Antarctica's melting will eventually produce does not rise uniformly around the world's coastlines. The gravitational pull of a large ice sheet attracts ocean water toward it. When that ice sheet loses mass, the gravitational pull diminishes, and the ocean water that was attracted to Antarctica spreads out across other ocean basins. At the same time, the land beneath the ice sheet, relieved of its weight, rises through a process called glacial isostatic adjustment. The combined effect of these forces is that sea level rise from Antarctic ice loss is not uniform. It is highest, counterintuitively, in the regions farthest from Antarctica, including North America and Northern Europe. Coastal cities in the Northern Hemisphere will experience more sea level rise from West Antarctic ice sheet melting than coastal cities in the Southern Hemisphere will. This geographic pattern of sea level rise, derived from the gravitational and rotational physics of ice sheet mass loss, is one of the more counterintuitive and consequential pieces of information in sea level science, and it is almost never communicated in popular discussions of Antarctic ice loss. That is a story for another time. We started with a number. 1,788 million square kilometers of Antarctic sea ice on February 21. Size of Egypt, and through the winter months of 2023, the anomaly grew to 33 million square kilometers below average, twice the size of the previous winter record. A 5 standard deviation event that the British Antarctic Survey estimated would occur roughly once in 2,000 years in a pre-industrial climate. A result that THC-MIP-6 climate models do not reproduce, but the summer minimum was not a single-year extreme. The 2024 summer minimum tied for the second lowest on record. The 2025 summer minimum also tied for the second lowest. In 4 consecutive years since 2022, the Antarctic sea ice summer minimum has been below 2 million square kilometers, territory that had never been reached before in the satellite era until 2022. Then, we followed 3 specific physical processes that the standard models missed. The 3-phase sea ice collapse mechanism. The disruption of ocean stratification by wind anomalies, the ocean surface warming and ice albedo feedback, and the persistence of the new lower ice regime. And the consequences. An unprecedented doubling of midwinter ocean heat loss to the atmosphere in the regions of strongest sea ice loss, altered storm frequencies, changes in Antarctic bottom water production, and most directly relevant for the glaciers, warmer ocean water with greater access to ice shelf fronts. The seawater intrusion beneath Thwaites, documented by ICEYE satellite data from March to June 2023, showing ocean water reaching 6 kilometers beneath grounded ice at tidal frequencies, in a process no glacier model included. Intrusions 5 to 10 centimeters thick at tidal frequencies, reaching ice that every model treated as fully buffered from oceanic influence, and then confirmed in data from March 10-12, 2024, to have expanded into a fully connected 12-kilometer zone of continuous ocean ice contact. And the melt from below confirmation, the East Antarctica paleoclimate finding, documenting that warm ocean water drove rapid ice loss 9,000 years ago across East Antarctic coastal margins, in the same physical mechanism that is currently threatened. In the West Antarctic Ice Sheet. The evidence that the stability of Antarctica's larger and previously less worrying ice sheet may be less robust than assumed under conditions of warm ocean access. We saw the more than 100 scientists, 7 years, 50 million, conclude that Thwaites is set to retreat further and faster than previously projected, and that general West Antarctic ice sheet collapse cannot be ruled out. And, at the end, we arrived at what these three anomalies together reveal. The models that project sea level rise were built without three physical processes that are now documented as active and significant. The revisions those models need all point in the same direction: more ice loss, faster, and less certainty about the timeline than the current projections suggest. The ice is not following the known pattern because the known pattern was assembled from incomplete information. The more complete information now exists, and it is alarming. Why Antarctic sea ice transitioned abruptly in 2015-2016, after growing for 40 years despite global warming, remains incompletely explained. The three-phase mechanism identified in the Science Advances paper describes what happened. The deeper question of what specific trigger initiated the transition, and whether the sea ice could recover toward its historical average or has entered a permanently new state, is unresolved. Research published in Communications Earth and Environment characterized this as a potential shift to a new sea ice state driven by subsurface ocean warming. But the permanence of that shift is not confirmed, and the causal chain from global warming to the specific timing of the 2016 transition remains under investigation. The specific magnitude of the revision to sea level projections that the seawater intrusion finding requires has not been quantified in a revised model. The process has been documented observationally, and the March 2024 ICEYE data showing a 12-kilometer sea connected zone adds to the observational case. But the resulting change in projected sea level contribution from Thwaites in centimeters by 2100 has not been published. That calculation is the work that the field now needs to do. The vulnerability of East Antarctic ice shelves to warm ocean incursion under current and projected warming is an active area of research, with the paleoclimate finding from November 2025 providing historical context. The specific oceanographic changes, THA-T, would be required to produce present-day warm water access to East Antarctic ice shelves, and the timescale over which those changes might develop are not fully characterized. The subglacial hydrology dataset, published in February 2025, needs to be incorporated into ice sheet models and the resulting effects on ice dynamics quantified. This modeling work is ongoing, and the specific timeline for Thwaites' retreat, which the IEA characterizes as set to occur faster through the 21st and 22nd centuries, remains defined by wide uncertainty ranges. The urgently needed further research to refine this timeline faces institutional headwinds from potential funding cuts to U.S. polar science programs, including potential cancellation of the research icebreaker, Nathaniel B. Palmer, which would significantly reduce the ability to conduct the ship-based oceanographic measurements beneath Thwaites and around the rest of Antarctica that the IEA work has demonstrated are irreplaceable. First, model gaps are not the same as model failures. The glacier dynamics models that did not include the seawater intrusion process were not wrong in their approach. They were built on the best understanding of the physical processes available at the TIM-E. The ICEYE satellite constellation did not exist when those models were constructed, and the daily repeat radar data it provides was the enabling technology for the discovery. The models will be updated. This is how science progresses. But it means that the sea level projections generated by those models carry an uncharacterized uncertainty. The unquantified contribution of processes that were not known to be operating at significant magnitude. The specific finding that the process is expanding, with the 12-kilometer connected zone in 2024 data, means the revision will need to be substantial. Second, 5 standard deviations is a statistical statement about how unusual an event is within the observed record, and it carries a specific scientific meaning that popular coverage typically obscures. A 5 sigma event is not simply a very large anomaly. It is an event whose probability, within the distributional assumptions of the historical record, is approximately 1 in 3 million per year. The British Antarctic Survey's finding that the 2023 winter anomaly would occur once in 2,000 years in a pre-industrial climate reflects both the magnitude of the anomaly and the fact that climate change has made such anomalies more likely. Understanding why it occurred, specifically the three-phase mechanism documented in the Science Advances paper, is more important than the statistical characterization, because the mechanism is what allows scientists to assess whether the event was a transient outlier or the first manifestation of a new, lower ice regime. Third, cannot be ruled out, has a specific scientific meaning that is frequently misread in both directions. It means that the evidence base is insufficient to exclude the possibility, not that the possibility is likely or imminent. The statement Thwaites general collapse cannot be ruled out over the 21st and 22nd century timeframe means that the evidence assembled over 7 years does not allow confident exclusion of this outcome. It does not mean it is the most likely outcome, and it does not mean it will happen on any specific schedule. The same scientific approach that produces cannot be ruled out statements also produces full collapse is unlikely in the next few decades. The second half of the own statement, which received less coverage than the first half. Fourth, the direction of revisions matters as much as their magnitude, and the consistent direction of multiple independent revisions is itself a scientific signal. Each new finding about Antarctic ice loss has revised the projections in the same direction. More ice loss, faster. The seawater intrusion paper adds ocean ice contact area to the models. The summary adds observational confirmation of accelerated retreat. The subglacial hydrology dataset adds improved understanding of basal dynamics. The St. Antarctica paleoclimate finding adds historical evidence of ocean-driven instability in a region previously considered stable. Each of these adds to a consistent signal, even before the specific revised numbers are published. When multiple independent research programs, using different methods and studying different aspects of a system, all find that the system is more vulnerable than the models assumed, that convergence is meaningful. Fifth, the geographic pattern of sea level rise matters for policy in a way that is rarely communicated. Sea level rise from Antarctic ice loss is not uniform globally. The physics of ice sheet mass loss, changes in gravitational attraction as ice is lost, changes in Earth's rotation, and land uplift beneath the retreating ice, produce a specific spatial pattern of sea level change. When the West Antarctic Ice Sheet loses mass, its gravitational pull on the ocean decreases. The ocean water that was attracted toward Antarctica by that gravitational pull disperses, raising sea levels preferentially in the northern hemisphere. Coastal communities in North America and Northern Europe will experience substantially more sea level rise from West Antarctic melting than communities in the Southern Hemisphere will. For coastal cities like New York, Boston, London, and Amsterdam, the sea level rise contribution from Thwaites and the broader rise is amplified relative to the global average. This geographic pattern is derivable from basic physics and is reasonably well established in the scientific literature, but it is almost never communicated to the communities whose planning decisions depend most directly on it. The CMIP-6 climate models did not reproduce the 2023 Antarctic sea ice anomaly. These are the same models that underlie the IPCC 6th Assessment Report projections for sea level rise. What should policymakers do with projections when the models generating them have a documented failure to reproduce a recent, major observed event? Is the appropriate response to wait for revised models before acting, or to apply precautionary principles given the consistent direction of revision? The IAEA spent 7 years and $50 million to conclude that Thwaites retreat cannot be stopped, and that general wise collapse cannot be ruled out. Sea level projections used in coastal planning were generated without the key physical process, the IAEA identified as operating. At what point does the gap between what the science has found and what the projections include become a policy problem, not just a research problem? And, on the broadest level, Antarctica is one of the most remote places on Earth. The physical changes happening there will not directly affect the lives of the scientists studying them until those changes have altered sea levels enough to affect coastlines. What does it mean to study, in careful detail, a system that is changing in ways that will matter enormously to people who are not yet born? And what obligation does current understanding of that system create for current generations? If this one stayed with you, let us know which part landed hardest. The 5 sigma winter sea ice anomaly, and what it means that the models didn't predict it. The ICEYE satellite data showing seawater reaching 6 kilometers beneath Thwaites' grounded ice in a process no glacier model included, and the 2024 data showing that zone expanding to 12 kilometers. The 7-year conclusion. Retreat is set to be faster, wise collapse cannot be ruled out. The East Antarctica finding. The ice that was said to be stable also showing historical ocean-driven vulnerability. Or, the framing at the end. The known pattern was assembled from incomplete information. The more complete information now exists, and it points in one direction. And, if you want more of his real Earth system science told at the level of the specific physical mechanisms, subscribe to Galaxy Pulse, and we will see you in the next one. In February 2023, the Southern Ocean was missing a patch of sea ice larger than Egypt. By winter, the anomaly had grown to twice the size of the previous winter record. The models didn't predict it. Beneath Thwaites Glacier, seawater is reaching 6 kilometers under grounded ice at every high tide. By March 2024, that zone had connected to the grounding zone, 12 kilometers of ocean under ice. The models didn't include it. After 7 years and 50 million studying the most important glacier on Earth, more than 100 scientists reached their conclusion: retreat will be faster. Collapse cannot be ruled out. The glacier melt happening right now is not following any known pattern. Because the pattern, the full pattern, is only now being found. A note on what it means to monitor a system at this scale. There is one more dimension to the Antarctic story that deserves explicit attention, because it connects the specific scientific findings to a broader question about how the scientific community manages knowledge about systems whose behavior is consequently on civilizational timescales. The Antarctic ice sheet contains enough ice to raise global sea levels by more than 58 meters if it melted entirely. This is not a scenario that is projected to occur. The ice sheet will not melt in any timeframe relevant to planning decisions currently being made. But even small fractions of this total, the 0.6 meters in Thwaites, the 3+ meters in the full West Antarctic Ice Sheet, the larger amounts potentially associated with East Antarctic marine sectors, represent changes that would reshape coastlines globally and displace hundreds of millions of people over the course of the century or centuries in which they occur. The decisions that determine how much ice is lost, primarily the decisions about how quickly the world decarbonizes and stops adding greenhouse gases to the atmosphere, are being made now. In the next decade or two, the consequences of those decisions will play out over centuries. The ice sheet's response to the warming that has already occurred, and to the warming that will occur before any decarbonization can take effect, is already underway. The seawater intrusion beneath Thwaites is happening now. The grounding line has already retreated. The question is how fast and how far the retreat continues, and that depends on how much additional warming occurs. This is the context in which the three anomalies described in this video are most significant. They are not alarming because they indicate an imminent catastrophe. They are alarming because they indicate that the system is already more deeply engaged with the warming it has experienced than the models assumed, and that the decisions being made now about emissions will determine whether the system stabilizes at a bad outcome or continues toward a much worse one. The own explicit recommendation that immediate and sustained climate change mitigation offers the best hope of delaying ice loss is not a political statement. It is the scientific community's assessment of what the evidence about Thwaites' behavior implies for what kinds of actions can still make a difference. The three anomalies are data points in a system that is already in motion. Understanding that motion, in the physical detail that the PNAS seawater intrusion paper and the summary provide, is what responsible engagement with the science of sea level currently requires. The question of scientific communication and uncertain timelines. There is a tension in Antarctic science communication that is worth naming directly. The most alarming version of the Thwaites story, the Doomsday Glacier framing, overstates certainty about timelines in a way that the evidence does not support. The explicitly states that full collapse is unlikely in the next few decades. Individual dramatic events, like ice shelf calving or unusually rapid grounding line retreat in a given year, do not represent the beginning of runaway collapse. The story of Thwaites is a story of decadal to centennial change, not imminent catastrophe. The most reassuring version of the story, the models show this will be slow and manageable, understates the significance of the specific model gaps now identified, treats the IPCC projections as more reliable than the current scientific evidence supports, and overlooks the consistent direction in which every new finding has revised those projections. The honest position is the one the has articulated. The retreat is accelerating, it will go faster than the old models predicted, and the possibility of outcomes much larger than the central projections cannot be excluded. This position is genuinely difficult to communicate, because it is neither alarming in the headline sense nor reassuring. It is alarming in the actuarial sense. The probability distribution of outcomes has shifted in a direction that makes precautionary action more warranted than the pre-2023 sea ice anomaly science suggested. The three anomalies described in this video are part of a process by which the scientific community is characterizing, with increasing precision, a system that will shape coastlines for centuries. The characterization is not complete. It is far more complete than it was 3 years ago, and it points, consistently and without exception, in the direction of more ice loss, faster than the models that generated the projections currently used by coastal planners and policymakers assumed. That gap between what the science now shows and what the planning frameworks currently reflect is not the fault of the planners. The science moved faster than the planning frameworks. That is a normal feature of how scientific knowledge about complex systems advances. But the gap exists, and closing it requires communicating clearly about what the three anomalies actually found, what they mean for the reliability of existing projections, and what the range of outcomes that cannot be excluded implies for decisions being made now about infrastructure, coastal development, and climate mitigation. That is what this video has tried to do. And that is why the glacier melt happening in Antarctica right now deserves the specific, mechanistic attention that the headline summary cannot provide.